Welcome back to Code Meets World. Today we're going to be looking at another problem in the bit manipulation category, which is, in this case, the counting bits problem. So we're told that given an integer n, we need to return an array that's length n plus 1, such that for each I, so for each number between 0 and n, the array that we return includes the number of ones in the binary representation of I. So that's a really confusing prompt. But what I think it's saying is that, say we're given n equals 2. According to the instructions, that means for every number between 0 and 2, so in this case 0, 1, and 2, we need to take the binary representation of each of those three numbers, which is shown here, and then count how many ones are in each of those binary numbers and put that into the array. So 0 has no ones, so we put a 0 in the first place in the array. 1 has one 1 in its binary representation, so we put a 1 there. 2 in binary is 1, 0. That has 1, 1, so we put a 1 here. It's the same thing with 5, except we just do this for every number between 0 and 5. And we put how many ones are in each of those binary numbers. So the binary representation of 3 has 2 ones in it, so that's why there's a 2 here. 4 just has 1, 5 has 2 of them. So that's the problem. Let's go down to the whiteboard and talk about how we might solve this. Okay, so this is a fun one. This is kind of interesting, and actually, if you haven't watched my last video, I'll link it at the top right now. But I actually sort of solved this problem last time. And in that video, I was just counting how many ones are in the binary representation of a given number. So one way that we could solve this is to do literally exactly what I did last time, but do it for every number. So last time there was an algorithm, and again, watch the last video if you'd like to see how I did this. But there's an algorithm where you can count how many ones are in a binary number by simply taking whatever that number is n and anding it, a binary and, with the number 1. And this tells you is, I'm going to say RMB, the rightmost bit, a 1. So you can tell if there's a 1 in the rightmost bit. This would be the rightmost bit in a binary number. And then 2, you could say n bit shift 1, which chops the rightmost bit off. And so then you're considering the next bit, the next time you go around. And using this little formula, you can loop through a binary number and count how many ones are in it. So one way that we could solve this problem today is by applying the algorithm from last video to each of the numbers that we need to loop over. So for example, for n equals 5, we would just run this algorithm 6 times for 0, 1, 2, 3, 4, and 5. So we would just run the algorithm 6 times, each one would count the number of ones, and we would return that. And I think that would work perfectly fine. However, I don't think it's the best solution in this case, because you have to loop over all n numbers, and then for each of them you have to loop through the binary for all of them. And there's a better solution, because there's a really interesting trick that I think we can use here that'll allow us to solve this problem with dynamic programming plus bitwise operations. So let me show you what I mean. If I write out all the binary numbers between, let's say, 0 and 8, if you haven't seen this before, I'm just going to write them out. And the reason I'm doing that will become clear in a second. But there's a pattern that we can pick up on that's only obvious, I think, when you can actually see them all at once. So I'm on 5. This is 6. This is 7, and last but not least, that's supposed to be a 1. That's 8. So again, this is 0, 1, I'll make a little line here. 2, 3, 4, 5, 6, 7, 8. Sorry I took all the time to write that out, but I think this is really important to see. You'll notice a really interesting pattern here. If we take any of these binary numbers and look how many 1s are in them, so for example, let's take 6. There are 2 1s in the binary representation of 6. What's really interesting is this is the same number of 1s as what's in half of the number. So 6 has 2 1s. You can see that 3 also has 2 1s. This pattern holds for other numbers too. If we look at the number 8, it has 1 1 in it. Sorry, my pen's not working. It has 1 1 in it. Half of 8 is 4. We see 4 has 1 1 in it. Half of 4 is 2. There's 1 1 there. Half of 2 is 1. There's 1 1 there. So that makes sense for the even numbers, but what about an odd number? So for 7, if we take half of 7, that's 3.5. But in programming, if we just do integer division, whatever's on the end gets cut off. So 7 divided by 2 equals 3, not 3.5, if we're doing integer division. So 7 divided by 2 is actually 3. So 7 has 1 1 in it. But if we go down to 3, or sorry, 7 has 3 1s in it. Sorry about that. 7 has 3 1s in it. But if we take half of 7, that's 3. We go down to 3. That one only has 2 1s in it. So we would have to add 1 here. Why am I telling you all of this? Well, that's because the pattern here is a known pattern, and that is that for any binary number n, if it's even, the number of 1s in n is equal to the number of 1s in n divided by 2. This is for even. If it's odd, the number of 1s in n is equal to n divided by 2 plus 1. This is the secret to this problem, because we can do this using dynamic programming, just looping through all the numbers one time. So we know that 0 has no 1s in it. We know that 1, the binary representation of 1, has 1 1 in it. Because we know this, we can solve any other number. Because for number 2, we know that there's 1 1 in 2. But using our little formula, we can say, okay, 2 is even, so the number of 1s is equal to n divided by 2. So the number of 1s in the binary number 2 is equal to the number of 1s in the binary number 1. Well, we already have that. We already calculated that right here. So we know that this one is 1. For 3, if we do 3 divided by 2, we get 1.5, but we cut off the decimals, so we just get 1. So the number of, using our formula, the number of 1s in the binary number 3 is equal to the number of 1s in the binary number 1 plus 1. So that would give us 2. And we can see that that's correct based on our chart here. Hopefully this makes sense, but now we're going to write the code to make this work. Based on what we saw there, this code should actually be fairly straightforward, I think. The first thing we can do is create our solution array. And I'll just make that empty and we'll append to it as we go. From there, what I think I can do is, let's see, the instruction said length n plus 1. So for I in range n plus 1, we need to check a couple of things. If I is 0, we know that the binary number 0 has no 1s in it. So we can say solution.append 0. Another case is if I equals 1, we know that we can append to the solution the number 1, because the binary number 1 has 1 in it. That's always hard to say. Once just like I showed on the whiteboard, once I've initialized 0 and 1, I can calculate anything else dynamically. So all I have to do is check if it's even or if it's odd, and then I need to look up in my array what n divided by 2 is, and then either add 1 if it's odd or don't add anything if it's even. So I'll do odd first. I can say if I modular division 2 equals 1, so this means if I is odd, and actually I don't even need the equals 1 because that just returns true. So rather than checking if it equals 1, we just say if this is true, meaning if this is 1. So if I is odd, we need to say that solution dot append, and then we can say solution if I integer division 2 plus 1. So this is exactly that formula I was talking about on the whiteboard. If the number is odd, the number of ones in the binary representation of that number is the exact same as the number of ones in half that number plus 1. And then finally, the last case, which is if I is even, is exactly the same. Solution.append, solution I integer division 2, but this time we don't need to add the 1, because as I showed, 8 is the same as 4, which is the same as 2, which is the same as 1. And then at the very end, I think I just need to return the solution. Let's run this, see if it works. It's taking a while, and that's because I forgot my colon. Sorry about that. Okay, wonderful. So that's working for both of them. I'm gonna go ahead and submit it. I'm feeling confident in this solution. All right, nice. So that's worked. We're at the 98th percentile runtime. Pretty good memory as well. I'm not too concerned about that. But yeah, this is a really quick solution. It's able to go through it in O of n time, which is really good, as fast as you can do for this problem. And yeah, hopefully this is a neat little binary trick that you didn't know before. I'll see you next time.